Good evening, everyone. So in the last class, we had discussed about the glass transition temperature, and one of the main aspect that we had discussed was that the amorphous state can exist in two forms, but that is the supercooled liquid state and the glassy state. The supercooled liquid state occurs above the glass transition temperature, and the glassy state occurs below the glass transition temperature, or the TG. And the main difference between the two was that supercooled liquid is more like a rubber-like state. That is why it is also called as a rubbery state. Whereas the glassy state, or in the glassy state, the material looks like a solid glass. And we had taken the example of window glass that we normally see. We are now going to move forward to another important concept in today's class, and we are going to try and answer one question: that why does TG take place? Or we can reframe it in the other sense that when we are cooling the molten material quickly, what would happen if the glass transition temperature does not take place and the liquid keeps on cooling on the equilibrium line? So just to put the concept in the right perspective, I'll go back to one of the previous slide that we had used. And what I am trying to convey here is that this was the crystalline state. When we heat it at the melting point, there is a sudden change in its properties, and then it becomes liquid or molten. And when we start to cool this molten form, the liquid enters into the supercooled liquid state, and at some point it deviates from this equilibrium line into a new non-equilibrium state called as the glassy state. So the question that we are trying to address is that what would happen if this deviation does not take place during this cooling curve? So this is an important aspect that we have to look into. Please keep another thing in the mind, that on this axis we have the temperature, and on this axis we have the volume or the enthalpy. We can also have on this axis other thermodynamic properties like entropy or the free energy. So we can additionally write at this axis entropy and free energy. We will be using those terms in our subsequent discussions. So that is why I am pointing out that this axis could also mean to be entropy or the free energy. So I'll go back to the earlier slide that we were discussing. So coming back to the question that what would happen if the TG did not take place, a very short answer to this is that glass transition temperature, or TG, is a thermodynamic necessity, and we will try to understand why we are making this particular statement. Glass transition temperature is a thermodynamic requirement for a supercooled liquid, since without such a transition, the amorphous material would attain a lower enthalpy than the crystalline state and ultimately will attain negative enthalpy. This critical temperature at which this would happen is called as the Cosman temperature, or the TK, and is thought to mark the lower limit of the experimental glass transition temperature, and to be the point at which the configurational entropy of the system reaches zero. So I'll go back to the original picture, or the original diagram that I was using to explain this particular concept. So what we are saying is that if you were cooling the material and it enters into the supercooled liquid state, and remember it is in equilibrium with the liquid state because it is following the straight line up to this point, assuming that this deviation or a subsequent deviation of the TG does not take place, then the liquid will follow this dotted line as the path, and at a point it will meet the crystalline curve. So this is called as the Cosman temperature, and at this point the enthalpy of the glass would become equal to that of the crystalline state. And if it continued falling down, the enthalpy will become negative with respect to the crystalline state. And this lower limit, as we had discussed, from up to which the glass transition temperature has to take place, is called as Tk, or the Cosman temperature. So this is one argument, that if this deviation does not take place at a particular point, the glassy state will have negative enthalpy with respect to the crystalline state, which simply means that the glassy state will now have a enthalpy which is lower than that of the crystalline state. So this was the first argument, which is related to Tg being a thermodynamic necessity. But there is even more compelling argument, which is in terms of the entropy. And this particular phenomena is called as the entropy crisis. We'll try to understand this concept. If the specific heat did not drop at Tg, and the rapid decrease of the liquid entropy were to continue, then liquid will have the same entropy at the crystal once the Cosman temperature is reached. Below this, the crystal will have a higher entropy than the glassy state. In other terms, the glassy state will have a lower entropy than the crystalline state. Although it is counterintuitive, that is against the normal logic, that a liquid could have an entropy smaller than an ordered crystal, but it does not violate any law of thermodynamics. So it can be possible, because it is not violating any law of thermodynamics. However, the third law of thermodynamics would be violated if liquid entropy continued to decrease much below the Cosman temperature without any change in the slope. Since then we find that entropy, that is S, becomes negative much above T is equal to 0, that is absolute 0. The third law of thermodynamics states that the entropy of a pure crystalline substance is 0 at absolute 0, because the crystal arrangement must show the greatest orderliness at this temperature. So what is happening is that this third law of thermodynamics is getting violated if the entropy continued to decrease much below the Cosman temperature without any change in the slope. So I'll again go back to the same picture to discuss this particular point as well. Remember, I told you on this axis you can also have free energy or entropy. So what we are saying is that when this liquid is being cooled, the entropy is also decreasing, and if this deviation does not take place, it will follow this particular dotted line, and the entropy of the liquid will become so the entropy of the liquid will become equal to that of the crystalline material. And if this keeps on falling further, this line will meet the x-axis somewhere here, which means the entropy has become 0 at a temperature which is higher than the absolute 0. So if the entropy becomes 0 at a temperature higher than absolute 0, the third law of thermodynamics is getting violated, and since it is a law, it cannot be violated, because all the laws that exist in the nature can never be broken. It's not a rule, it is a law. So to preserve the law of thermodynamics, and more specifically the third law of the thermodynamics, which means that the entropy of the system is 0 at absolute 0, it cannot be 0 at a higher temperature than absolute 0. So to preserve this third law of thermodynamics, this deviation of the equilibrium line during the cooling of the liquid has to take place. in nature this will take place. If it does not take place here, it will take place somewhere here, or here, or here, or here, and it has to be at a temperature which is greater than the Tk. So I'll go back to the previous slide. Yeah, so we were trying to convey here that the third law of thermodynamics would get violated if liquid entropy continued to decrease much below the Boltzmann temperature as well. So these are the explanations which basically give us the idea that why there is always the possibility of the glass transition temperature taking place, which means glass transition temperature will always take place at some temperature which is higher than the Boltzmann temperature, because if it does not take place, the third law of the thermodynamics will get violated. So we'll now move over to the next aspect, which is the experimental measurement of the glass transition temperature, which means that if you have been given a amorphous sample, how you will determine its glass transition temperature. There are various ways, which means there are various analytical tools that can be used to do this measurement. And the most common one is the differential scanning calorimeter, or what we call as DSC. When the TG is measured using the DSC, it is called as the calorimetric TG. You can also use viscometer for measurement of the TG. You can also use dielectric spectroscopy. You can also use dynamic mechanical thermal analysis for measurement of the TG. In those cases, you will have to mention the technique which has been used for the measurement of the TG. Interesting aspect is that if you measure the glass transition temperature of the same material using different analytical tools, you end up with different values of TG. So we'll come to that aspect later as well. So here we'll try to understand some important aspects related to the experimental measurement of the glass transition temperature. The liquid means the supercooled liquid to glass transition is an atypical phase transition. Atypical means it does not look like a typical phase transition like melting point or melting phenomena. So this is an atypical phase transition that in that it is not connected with a discontinuous change in the structure, and in that it does not have a sharp transition temperature. Melting point in a DSC, if you remember or if you have ever done, is a very sharp transition, which means it occurs over a very small range of temperature. Usually it will happen in 2 to 3 degrees Celsius range. In contrast to that, TG occurs over a wider range of the temperatures. There is a rather glass transformation range that extends over several Kelvin or more. This could also be several degrees Celsius or more. Upon cooling or heating through this range, one observes a smooth step in the thermal expansion coefficient and in the specific heat. The exact temperature where these effects are observed depend, however, on the temperature variation rate, which means the heating rate that has been used or the cooling rate that has been used will impact the value of the TG that you measure. And in more general, you can say it is dependent on the preparation protocol that you use in that particular analytical technique. So as I told you, it is commonly measured using thermal technique like DSC, and this TG is called as the calorimetric glass transition temperature. Calorimetric TG is defined as the onset or the midpoint of the step change in the heat capacity. We'll see this with the help of an example in the next slide. There is no international convention on this subject, and TG is usually determined in a heating cycle mostly at 10 degrees Celsius per minute or 20 degrees Celsius per minute. So this is an example of how a calorimetric glass transition temperature looks like when it has been measured using either a differential scanning calorimeter or a modulated differential scanning calorimeter. So this is the enthalpy and this is the temperature. So as you are moving from the glassy state into the supercooled liquid state by heating the sample, there occurs this step change in the specific heat. And the point where it starts is called as the onset TG. And if you draw a tangent here, and then a straight line here, the midpoint of this would be called as the midpoint or inflection TG. And this would then be the supercooled liquid state. Now, the interesting aspect here is that we have discussed here measurement of the TG when we are heating the amorphous sample. And suppose the sample has been heated, it has entered into the supercooled liquid state. If you then cool it back, which means you follow the reverse path now, the TG will again occur at the same point. So, which means if you keep on heating and cooling the sample consecutively or alternatively, the TG will keep on happening at the same point. Because of this, the glass transition temperature in the modulated DSC occurs in what we call as the reversing heat events curves, which means it is a reversing event, which simply means that it keeps on reversing as you heat and as you cool the sample. Calorimetric TG is defined as the onset or midpoint of the step change in the heat capacity. So in some of the research papers, you will see the researchers will report the onset TG. In other cases, they will report the midpoint TG. And as discussed earlier, TG is usually determined in a heating cycle, mostly at 10 or 20 degrees Celsius per minute. But I repeat that you can also determine the TG in the cooling cycle, assuming that you were already in the supercooled liquid state. This is one case study or an example of the data which has been generated in NIPER itself, and the material that was taken for the study is pure curcumin, and it involved determination of the TG of pure amorphous curcumin. There are three heating curves that are shown here. So we'll first see this middle one. So this is for the crystalline curcumin form 1. So curcumin can occur in two polymorphic forms, form 1 and form 2. So when you heat the crystalline sample, you see that it keeps as a straight line and then it suddenly melts. So this is the melting event for the form 1 of curcumin. If you take the sample of curcumin and you heat it beyond its melting point and then suddenly cool it in the DSC, which means all the activity is being done in the DSC sample holder cell itself, then you get amorphous curcumin, written as CRMA, and we call it in situ amorphous curcumin because it has been formed within the DSC cell. And if you heat that particular sample, you see a very subtle transition taking place here, or a very small thermal event taking place here, and thereafter there is no event and this straight line continues. Why? Because this is the amorphous sample and the amorphous sample obviously will not show any melting point because it has converted to the amorphous form. Now this event which you see here, if you enlarge it, it looks something like this. So this is the in situ curcumin amorphous. So this is the onset of the TG. This will be the midpoint. So this is the glass transition temperature of curcumin seen during the heating curve. Now, instead of making the amorphous curcumin in situ in the DSC, if you prepare it outside, say in a beaker by heating it on a hot plate and then cooling it in a, say, liquid nitrogen, we get a sample of amorphous curcumin, which we will call as XC2 amorphous curcumin. And if you heat that sample, you again see this small subtle event, which is indicative of the glass transition temperature. And subsequently, you see this exothermic event. So this was an endothermic event, and this is an exothermic event, which is followed by the melting event. Now, what this indicates is that the ex-situ sample tends to crystallize during the heating phase, and that crystallized material will then melt in the DSC heating. So this is the melting point of the crystalline curcumin. So if we look at this event in the enlarged version, you can see the XC2 curcumin or the amorphous curcumin shows the TG at 57.21 instead of 69.49, which was shown by the in situ sample. This is basically because when you prepare the curcumin amorphous form XC2, some moisture from the atmosphere gets incorporated into the sample, and the glass transition temperature of the water is very, very low. It is somewhere around minus 137 degrees Celsius. Because of that, the overall TG of the amorphous curcumin has fallen from 69.49 to 57.21. And another important phenomena that is taking place in the XC2 sample is that it is recrystallizing during the DSC heating run, followed by the melting of the crystallized curcumin. Now you will also observe one difference here, that the melting point of the curcumin earlier was this much, because this is the form 1 of curcumin. But in this case, the crystalline curcumin shows a lower melting point. This indicates that the crystalline polymorphic form that you obtained during this recrystallization is the metastable form, and it has a lower melting point as compared to the stable form 1. Now, if you remember, we had discussed the Oswald's step rule, which had said that the solid form that you achieve first is nearest to the starting material's free energy, which means if you have the amorphous form, the first crystalline form that is going to be formed would be the one that is nearest in free energy to the amorphous form, which would be the metastable form. And subsequently, this metastable form will convert to the stable crystalline form. That is what the Oswald's step rule says. So in this case, we see that the metastable crystalline form of curcumin is appearing, although it is not showing conversion to the stable form during this DSC run. But if you slow down the heating rate, or if you store it for a reasonably longer period of time, it will convert to the stable polymorphic form later on. As I told you, apart from the DSC, you can also use a dynamic mechanical thermal analysis as a tool for determination of the TG. So in this tool, basically you are measuring the mechanical property of the material as it is being heated in the instrument. And what we get are these values. So this is tan delta, and it is the ratio of the storage to loss modulus, and is sensitive to molecular mobility. Thus, it can be used to characterize the glass transition temperature. Decline in E bar near Tg signifies initiation of cooperative molecular motions. We will discuss this concept later on in one of the slides. What just we are trying to highlight here is that this is the glass transition temperature that you get using the dynamic mechanical thermal analysis for amorphous silicoxib. So this is the crystalline silicoxib and this is the amorphous silicoxib. So it is occurring at a value of 72 degrees Celsius. Now, if I remember correctly, the glass transition temperature of silicoxib or amorphous silicoxib, if you determine by DSC, is somewhere around 60 degrees Celsius. Whereas here you see that it is occurring at a temperature which is much higher than the calorimetric glass transition temperature. So it again highlights that if you change the analytical tool for the determination of the Tg, the value of Tg that you get is going to be different. It could be slightly different and sometimes it could be very different. So after learning about how to measure the glass transition temperature, we move over to some of the examples where a table is given and the Tg values of some of the amorphous pharmaceuticals have been recorded. So the material could either be an API or it could be some excipient. You can see for naproxen, the Tg is -3 degrees Celsius, while on the other extreme you have atorvastatin calcium, which has a Tg of 140 degrees Celsius. The significance of this is the fact that higher the Tg value, more stable it would be at the storage temperature, that is the ambient temperature. So naproxen with a Tg value of -3 would not be stable at all if you store it at the room temperature. But if you look at atorvastatin calcium, which has a Tg of 140, so even the amorphous form of atorvastatin would be very stable or stable for a very long period of time at the room temperature. Similarly, cefuroxime acetyl has a Tg of 81. Griseofulvin has a Tg of 88 degrees Celsius. Glibenclamide has a Tg value of 62. If you recollect, atorvastatin calcium is also sold as a amorphous API in the market. Similarly, cefuroxime acetyl is also sold as amorphous API in the market. So the reason for this is that since they have a relatively high Tg, they can remain stable for a long period of time at the room temperature at which they are stored. And these amorphous APIs can be used to generate or develop the dosage forms also, because they are going to remain stable at the room temperature. When we say stable, we do not mean that they are going to be more stable than the crystalline form. We are simply saying that at the room temperature or at the storage temperature, these amorphous forms are going to be stable for their shelf life. If you give severe conditions of storage and temperature, they will ultimately convert to the crystalline form. But at the normal storage with due protection from the moisture, these APIs can remain in the amorphous form. These are some of the excipients for which the Tg values have been given. So you have sucrose, lactose, trehalose, all of them are sugars and they have these Tg values. Whereas the polymers like PVP, K12, K30, K90 have these Tg values. Again, this is going to be discussed later as well, that these polymers which have high Tg value can be used as stabilizers for the amorphous form, because the total glass transition temperature or the overall Tg of a amorphous drug and this polymer which are present in the amorphous solid dispersion would be higher than the Tg of the drug alone. Say if I take the example of glibenclamide, which has a Tg of 62, if I mix one part of the amorphous glibenclamide with one part of PVPK30, which has a Tg of 160, the overall Tg of the system would be somewhere between 62 and 160. So it may become 100 degrees Celsius. So the amorphous solid dispersion would give much more higher stability to the amorphous glibenclamide, a concept that is used for designing of the amorphous solid dispersion. We will be discussing this later as well. The Tg can be estimated if you know the melting point of the crystalline material, and there is a rule called as 2/3 rule. And if you divide 2/3, you end up with 0.67. So Tg is roughly 0.67 times of the Tm or the melting temperature. And here are some examples given. So these are some of the materials. This is their Tg value. This is their melting point. And if you find out the ratio of Tg by Tm, you can see that you get a value which is close to 0.67. It may be slightly different as well because this is only a rule or a rule of thumb. This is not a law. So an important rule which can help you in determining what could be the Tg of a material if you know the melting point of the crystalline material. So we'll stop today's lecture at this point, and in the next set of lectures we will be studying the stability of the amorphous form, which is in fact a very important aspect. If you want to exploit the higher solubility of the amorphous form, you need to ensure that you have the stability of the amorphous form. Otherwise you will not be able to exploit it usefully. So coming back to the main points that we discussed in today's class. So first we discussed the reasons for why Tg always happen in nature. If Tg does not happen, there would be violation of the third law of thermodynamics, a fact which is also called as the entropy crisis. Then we studied about the experimental measurement of the Tg using the DSC, where the Tg is called as the calorimetric Tg. Then we took a couple of examples, and then we also looked at determination of the Tg using dynamic mechanical thermal analysis instead of THG, and we learned that depending upon the analytical tool that you use, the value of the Tg may be slightly or vastly different. Then we saw some of the examples of pharmaceutical materials and their Tg values, and the general important rule, what is called as the 2/3 rule for Tg, which says that the Tg is roughly 0.67 times that of the melting point. So we'll stop here and we'll take up the stability of the amorphous form in the next class. So thank you very much, and I look forward to receiving questions from you in the WhatsApp group that we have created. Thank you.